In this video, I want to review definite integral notation a little bit. This isn't going to be a new question about definite integral notation, but it's something that some students find a little bit uncomfortable, other students don't, but I just want to make sure that we're on the same page as we go into this next section. So take a look at this problem. All right, so we have a car driving down a straight highway from noon until midnight, and the velocity of the car at t hours after noon is given by the function v of t. So this is looking just like a traditional linear motion problem. So we want to give an expression for the distance the car traveled between noon and 6 p.m. All right, so pause the video. This is something that you should be comfortable with doing. All right, so between noon and 6 p.m. is between 0 and 6 hours after noon. And remember that when we're accumulating velocity, that gives us distance, or in other words, the definite integral of velocity gives us the change in position, the net change in position, which is essentially distance. All right, so this is the definite integral from v of t dt. So what are the bounds of this integration? All right, so we're starting at noon, which is 0 hours after noon, and we're ending at 6 p.m., which is 6 hours after noon. Okay, so it's like that, and that's all we're doing. All right, so now we want to give an expression for the distance the car traveled in the first t hours, where 0 is between p and 12. All right, so in some sense, we're creating a new function where t is the input. And if the input were 6, we would want this to be our answer. What would we do if 6 weren't the input? Pause the video and give that a thought. So it's really the exact same thing, except that it's the integral from 0 to big T of v of little t dt. All right, so the thing about this that some students find a little uncomfortable is that the input of this function, the variable in this function, is actually one of the bounds of integration. But this is something that is a completely legal thing to talk about. This is, a way of talking about how much stuff has been accumulating between the beginning of whenever we were noticing it and some fixed time t. To give you another example of a time when we use this, here is another example where we use a variable as one of the terms of integration. So the definite integral from 1 to x of 1 over t dt, where x is some number that that's greater than 0. All right, so we've talked about this as an integral that we know about, and this is equal to the natural logarithm expressed from, the natural logarithm of t expressed from x to 1. X is greater than 0, so we don't need absolute values around the t. So that's equal to the natural logarithm of x minus the natural logarithm of 1. Natural logarithm of 1, so this is just evaluates to the natural logarithm of x. So this is a way of writing the natural logarithm of x. And in fact, in some places where you see mathematics defined, this is actually given as the definition of the natural logarithm of x. So in those things, when we don't know about logarithms or exponentials ahead of time, you would look at this and say, well, we don't have an antiderivative for 1 over t because the power rule doesn't work. And so we say, well, okay, this should be a function, this integral, and so we're going to define this function to be the natural logarithm of x. So that happens sometimes when there are functions that we don't have obvious antiderivatives for, or we find out that the antiderivative is something that we've never been exposed to before. We will define a function in terms of its definite integral in this way. All right, so just to say that this is a legitimate way of talking about definite integrals, and we're about to be using this to talk about the other application of the fundamental theorem of calculus, which we'll start looking at in the next video.